Okay, so in any case, today we're going to finish up our use of the Poisson summation formula to get information about the heat kernel on the circle, right? So remember the setting, we had this thing, the Poisson summation formula. If you have something in Schwartz class, you create the periodization of that function, right? You take for each x, you take the function and you sum it at all, right? For every x, you sum it over all x plus an integer, right? You take the values of the function at every, x plus k, x plus n, where n is an integer, and that turns into that creates a continuous one periodic function called a periodization, right? And the Poisson summation formula says that, well, actually this is related to the Fourier inversion formula, in the sense that if you take sort of a discrete version of the Fourier inversion formula, and you don't take an integral, but you take some sort of only at the integer values, and you sum those guys, you actually get the periodization also. Okay, so this is the celebrated Poisson summation formula, and we said we're going to use it on the heat kernel for the circle to get to show that the heat kernel on the circle is an approximation of identity. So just to recall for those of you who maybe have forgotten, we have this thing plain capital H. The heat kernel on the circle, and using the integers, e to the negative 4 pi squared, n squared t, e to the 2 pi and x. We also have fancy h, t, the heat kernel on the line, which is this guy, 1 over 4 pi t to the half, e to the negative square root of 4. And this is the one which we had a lot of information about. We knew that this one was an approximation of identity. This is the one which we were not able to show as an approximation of identity, but we're going to do it today by using Poisson summation. Right. So last time we showed by the Poisson summation, we saw that in fact the heat kernel on the line was the periodization of the heat kernel the heat kernel on the circle, was the periodization of the heat kernel on the line. Right? So you take the heat kernel on the line, you periodize it, and you get the heat kernel on the circle. Okay. The corollary that we're going for is to show that the heat kernel on the circle is an approximation of identity as t goes down to 0 on the above. Okay. Okay. And so, when you were back then, when we were trying to use it to solve the heat equation, it actually does recover the heat equation. It does recover the initial data because it's an approximation of identity, right, as t goes down to 0. Right, you take the initial data and you convolve it with this guy. This is the good kernel, and so you can get that because it is what you want. Okay. Okay. So the proof is pretty cool. It's easy to see. So, to show something is an approximation of identity, remember what we have to do. We have to show that its integral is 1, right? We have to show that its L1 norm is bounded. The integral of its absolute value is bounded. And then we have to show that third property, that outside of any neighborhood of the origin, then the limit of the integral of the absolute value of the integral of the absolute value, goes down to 0. As t goes down to 0. Right, so it's easy to see that if we So this is a one periodic function. Here's a period. We're going to integrate over a full period, right? It's easy to see that this is one. You just use the uniform convergence, right? You're integrating over something of length 1, this guy, right, against dx, right? Well, each of these guys, you can, because of the uniform convergence, you can switch the order, right? So you can pull out the integral. Pull out the integral, and because you get summation integral, so n and c, e to the negative 4 pi squared n squared t, integral to the negative 1/2, right? Okay. But these guys are periodic functions on this period, right? So you're going to get 0 for everybody except when n is equal to 0. Right? The only term that's going to come out of this is the n equals 0 term. Okay, so you get e to the 0 and then 1. Right? The integral of 1. So you get 1. The end. Okay, so just because this is a uniformly convergent series, you can switch the order of integration and summation, and then that's the end. Okay, so that's actually easy to see. Okay. So that first one is easy, and then the second one, right? You want to integrate the absolute value of this one, right? And we just want to show that that's bounded by some constant, right? But we're lucky now. We use this bunch, right? So I think it could be sort of a pain, but look, if we look at this, we say, well, look, the heat kernel is a sum of positive things, right? Of positive things. So it's this is some positive number, and so we're done already by the first step. Okay. That I think that's not completely obvious, right? If I gave you this and I said, right, show me that for all x this is a positive number. Is that obvious? No, it's not obvious, right? It's not at all obvious. But thanks to Poisson summation, it's completely obvious. Obvious in the sense that after a lot of work, it's obvious. As you know already, people toss around terms like obvious or trivial very recklessly. Clearly is the one you got to watch out for, because clearly usually means that they're trying to hide something. Like particularly, it's almost a flag that says that the person is hiding something very hard. It is easy to see that. Well, okay. Anyway, I guess I say this all the time. Okay, so then the last thing we need to show is that if we take some eta, right, and we look outside of the eta neighborhood of the origin, right, we integrate. So here's 1/2, and here's negative 1/2, and here's negative here's eta, right? We have our kernel. We're hoping that for each eta, as t goes down to 0, most of the mass goes inside here. Right? Most of the mass goes inside the eta neighborhood. Right? So the mass outside should go to 0. In other words, this should go to 0 as t goes down to 0. Right? That's what we want to show. Okay. And so here's the trick. And this is a really nice thing to do. And you say, well, look, the heat kernel, we take n equals 0, and we get the heat kernel on the line, right? and then we have all the terms for n not equal to 0, right? So n not equal to 0. Right? So we use the Poisson summation to say that the heat kernel on the circle is basically the heat kernel on the line plus some error. Okay? And we call this error d. Okay? So, and we know that, we already know that, that HD is a good kernel. Right? So what we need to do is show that we already know that HD is a good kernel. So it suffices to show that that if we take that if we take the integral of the absolute value of dt over the whole range, then that this goes to 0. Right? Because if the error goes to 0, you know, if the mass of the error goes to 0, then we're just dealing with a good kernel. That's it. Okay. So here's our claim. So let's think about, before I make the claim, let me write up what ET is. And I should say maybe that when I was in junior high school, people called me ET. I forget. So let's think about this thing, right? The error is this 4 pi t to the half summation e to the negative x plus n squared over 4t n is not equal to 0. Right? Okay. In the notes I have n is in z star. When I say that, I mean n is in z, but not 0. Either way you want to write it. Okay. So, okay. So this is the error, right? This thing is the error, and we're going to claim that that et is controlled by some constant times e to the minus c over t. Okay. But this is basically, you know, e to the minus 1 over t. Okay, and this is actually pretty easy to see if you read the book and have somebody to show it to you. Okay, so so let's think for a second, right? This et, well, I'm just going to replace this by a c over root t. Okay. This first thing, I'm going to take a c here so I don't have to worry about writing 4 pi, etc. And then here, I'm going to say that this thing is bounded by e to the negative cn squared over t. Okay. And you can do this because x is small. Right? Right. So think of what's happening here. Right? You're taking this n, right? And you're adding some small x to it. Right? Well, if I let's see, so if I multiply n by some constant, right? So think like this, right? N plus x, right? right, is between n plus a half and minus a half, right? And n is not zero, right? So n is 1, 2, 3, 4, etc., right? Okay. Think like this. These are my possibilities. These are my possibilities for n, right? So when I add the x onto it, well, it's not going to move that much, right? Okay. Now this thing here is a decreasing function, right? So I multiply my n by, say, a half. Okay. Something slightly smaller than a half, right? So you notice that 1/2 n is less than or equal to this n plus x. Right? 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 1/2 n right? Let me just ignore the negative guys for now. It will work the same way for those guys, of course. Right? Does everyone see that? 1/2 n is definitely going to be smaller than or equal to n plus x, right? And so we can replace this thing by something smaller, right? And so the function gets bigger, right? Because it's a decreasing function. Okay. And so I take as my c is going to be 1/8. I'm sorry, 1/16. Okay. So take c 1/16. Is that clear? Anyone confused? Any? Right? We're trying to get an upper bound. We're trying to get an upper bound of this guy. This guy is a decreasing function. Right? This guy is a decreasing function. Well, I know the x plus n. The x plus n is bigger than a half n. I am asking you. You got it. Okay, good. Okay, so then I really keep on talking. Okay, so you get the symbol, right? Okay. Okay, and then we make the following observation, and then observe that then observe that, well, n squared, we have this n squared over t, right? N squared over t, let's say that, so assume that t is small, and t is between 1 and 0, right? Because t is going down to 0, so we can assume that, right? This is bigger than, so first is sort of dumb observation, n squared over t is bigger than or equal to 1 over t, right? Because n is not 0. So, n is not 0. Right. Second, not exciting observation, is that this thing is bigger than n. Because we divide by something smaller than 1. So those two observations together tell you that n squared over t is bigger than the average of those two, right? The average 1 over t plus n squared. Okay. Okay. And so now we get it. If we look at the size of the error, well, we have a c over root t summation e to the minus c n squared over t, but the n squared over t is bigger than that, so this thing only gets bigger if we fill in the 1/2 1 over t plus n squared. Right? this thing here that we bounded it by is smaller than this thing because of this estimate, right? And that allows us to separate out the 1 over t, right? So, right. So what we get then is this thing. So c over t, c over root t, e to the negative c of 2t. And we pull out this term, and what we have left is the e to the minus c n squared over 2. Okay, and that's the bound that we wanted, right? Because this thing is some constant, right? This is some constant c, right? And so we get that. Right, we get that. We get the bound. We get the bound that we want. Right, so we get this is smaller than some constant e to the negative c.
Is it obvious how we get rid of 1 over root t?
Let me think. No. No. Hold on a second. Hold on a second.
Is it maybe okay if that's an exponential and the c over square root t is a polynomial? Can we do a trick like that with that and say that the polynomial is going to go slower than the exponential, so it'll go to 1? I don't know, maybe not. Yeah.
Okay, let me think about it. Sorry, maybe it's not obvious. When I was in college, during my last year, I had a professor he was teaching us algebraic geometry, and like he would try to do everything in a completely novel way, and would sometimes it would work and sometimes it would mess up. And many of the classes he would say like, okay, sorry guys, and he went off. I sort of feel like that. Okay, let me think about it. Thank you for catching. I hope it's obvious, but let me think about it. Well, supposing that actually is obvious, then this would give us the desired result, right? Because then we'd be, you've got this thing, as t goes to 0, then this thing is decreasing very fast. So, right, but even if we have that, right? Even if you're right, Jennifer, right? Because it'll still work actually. Even if we don't have this, it'll still work because as t goes to 0, right? As t goes to 0, this thing is going to go to 0 much faster than the root t. Anyway, yeah, that's right. This thing is going to decrease much faster than this guy. And so the bound is going to be, this thing is pointwise bounded by something that goes to 0, Theta. Okay, thank you. Okay. Yeah, so we actually don't have that last bound, but we have the second last bound, which is there was another professor when I was a graduate student, and he just refused to take any questions and was a very nervous guy. And an old, I think he was at retirement or past retirement. And then he finished the lecture and he went he always managed to finish the lecture right by the door. And so there are different ways of lecturing. Calderon, the king of harmonic analysis, one of the kings of harmonic analysis. So this book is written by Stein, right? It's Calderon. They both students at Zeta. I didn't realize this, but I guess both Peppermans, the Pepperman, were students of Stein. Both Pepperman the older and Pepperman the younger. So Calderon apparently, being Calderon, would not use any notes at all, and would simply come in and say, okay, today we're going to talk about this, and then try and figure it out on the fly, right? Try to figure out everything, and just see. He would show people how mathematicians work, and he was so brilliant that he would figure out everything on the fly, right? And even if it was not completely good pedagogical presentation, you got to see how he worked. I think that must have been incredible. Unfortunately, I never. By the time I got to Chicago, probably at the time, I met him once or twice.
Did he go back to Argentina or?
No, he stayed. He stayed there. Yeah, he stayed. I think he stayed in Chicago. Yeah. But because of him, much of harmonic analysis is in Spain. In Spain and I wish I could Spanish. I go to Spain like every 2 years. Yeah, because of him and other people who he nurtured, other. So later I'm going to talk about wavelets. This thing which became hot in the 90s. Maybe I'll talk about wavelets next time, I'm not sure. But it became hot in the 90s. But and it actually developed like in several areas simultaneously. In the area of image compression, seismic exploration, and also in mathematics. But in mathematics, Calderon had really been working on it in the 60s. He'd been using it using something basically like wavelets to study so-called singular integral operators in the 60s. But in the 90s, it was rediscovered in this sort of practical sense. Okay, so a slight digression into another thing. And we're not really going to say much except introduce some terms that will show up later. And it's appropriate to introduce them at this point because they're related to the heat kernel and Poisson summation formula. So, okay, so just watch this. I don't think there's any point in writing this down. So for s greater than 0, you have this thing called the theta function, right? Theta function is defined like this. The sum from n equals negative infinity to positive infinity into the pi squared and pi n squared s. Okay. This thing is called the theta function. It turns out that Poisson summation applied to the function e to the negative pi s x squared and evaluated at x equals 0, gives you what's called a functional relation. Gives this relation s to the negative 1/2 theta, x to the negative 1/2 times theta over 1 over s equals theta of s. Okay, so there's this relation between the values of theta. Okay, this may look sort of reminiscent to you of something. Does this remind you of anything? Scaling the Fourier transform. Okay, so sort of, right? You've got this, right? You've got something like a dilation, right? Yeah. That makes sense because this is basically a statement about you've got the periodization and the inverse Fourier, the Fourier inversion formula. So yeah, I guess so. Okay, I don't know what this formula is used for, but I would expect that you could use it to sort of bootstrap your way into defining. No, you can't. Forget it. Okay. Okay. So we also define something called a theta function. So I was writing for the big theta. Theta z tau, and this is for z a complex number. Z a complex number and tau, a complex number whose imaginary part is greater than 0. We define this theta function to be summation the same range, e to the I n squared tau, 2 to the I n z. Okay, and the relation is that this big theta is a generalization of the little theta. And for us, significantly, the big theta is actually evaluated. The point is the heat kernel on the circle. Interestingly enough, and just to throw something even more tantalizing. It turns out that there's this relation that if you so I don't even know what this means. I'm going to write it. Okay. So this is the gamma function, which maybe you've seen before, the gamma function. This is the zeta function, the zeta function, right? The Riemann zeta function. You know, the celebrated, Grail, the Riemann, the Riemann hypothesis, the zeta function, right? And so there's some relation between the theta, zeta, and gamma functions. Okay, right? So anyway, so that's who knows, maybe this will make you feel like reading book 2 and book 3 of the texts, where you'll start to draw everything together, like how mathematics is all one big united thing. Okay. For those of you who are interested in this sort of thing, let me give you a reference. There's a famous book by Whittaker and Watson, and people usually call it Whittaker and Watson, but the actual name is A Course in Modern Analysis. Okay, and it's from 1902. It's called A Course in Modern Analysis, but this book is actually like a classic among classics. It is still printed today. I used it as an undergraduate. The professor chose it for a second semester complex analysis course, and it talks about so the different kinds of theta functions and et cetera, et cetera. So the fact that this book printed in written in 1902 is still printed today, gives you some sense of its significance. On the back, it says something like thousands of mathematicians have been introduced to the field by this book, and I think that's an exaggeration. Okay, so the last thing we're going to talk about today is this thing, the Heisenberg uncertainty principle from quantum mechanics. Okay, and we'll see how this is, basically a consequence of it's an observation using Plancherel's theorem. So I'm not so familiar with this, but let me say it the way I understand it. So the question is, to what extent can one simultaneously locate or determine the position and the momentum of a particle? And the answer is that you can't do both of them simultaneously. That is, if you know exactly the position, then you lose you lose your knowledge of the momentum, and vice versa. You can know both of them to some rough extent, but you can't know one of them. You can't know both of them to an arbitrarily precise extent. Okay, that's pretty bizarre, but it's actually a result of Fourier, which can be is a result that can be shown using Fourier analysis, using the Fourier transform. So in quantum mechanics, and like I said, I don't really know this, but in quantum mechanics, a particle has associated with it something called a state function. Which we'll denote by psi. Okay, and this thing is an L2 function, norm 1. And this thing basically governs so this thing governs the position of the particle. So we're going to pretend that we're in a one-dimensional world. Okay. So here's our world. It's only one-dimensional. I'm assuming that the same sort of thing holds in higher dimensions. But, okay. So what does the state function tell you? It tells you that the probability that the particle lies in some interval. Okay, it tells you the probability. That probability is just the integral of the absolute value squared over that interval. Okay. Okay. Right. If we integrate over the whole line, of course, we get 1. Right. That's to say that the probability of being in the line is 1. Right. Which is as it should be. Right. Okay. And then so this is a probability. This thing, you know. Then, if you're thinking about the expected position, well, the expected position denoted by x bar, well, you probably can guess how to figure it out. Right? You take the position times the probability that you're going to be in that particular position. Right? So this is like an expected value. Right? The probability that you're going to be in that position times the position. You take the sum of all those expected values, and you get the expected position. Okay. So this is the expected position, and as you probably know, in this thing, the variance, right, you look at the difference from the expected position squared. You get the L2 norm of that against the probability function. Right. This is measuring, you know, how much your function is deviating from the expected position. Right. If your function stays in its expected position all the time, then the variance is 0. Right. Okay. So here's the cool thing. Okay, so one has an analogous setup for momentum. Okay, but here's the interesting thing. It turns out that the probability of the momentum lying in AB is the integral of the Fourier transform over AB. state function governing the momentum is the Fourier transform of the state function governing the position. Okay. And like I said, I have no idea why this is true, but for some reason in physics, maybe somebody can tell us, the state function governing the momentum is the Fourier transform of the state function governing the position. Okay, so that's I don't know what that is. I should ask physicists to explain. Okay, so here's the Heisenberg uncertainty principle. That the variance of the position, times the variance of the momentum cannot be small, cannot be arbitrarily small. Okay. It's bounded below by some constant. The primary constant is involves Planck's constant, which I don't know. So okay. So what is it saying, right? That this is exactly right. You can't know both of these with arbitrary precision, right? Because that if you did, you'd be getting below this boundary. So there's some lower bound on the product of these things. Okay. And the reason that lower bound exists is just a consequence of basically Planck-Ross theorem. So this is cool. And this actually is important in what I was talking about earlier. Trying to decompose pictures or decompose sounds. Okay. I'll try to explain why that is later. But there's something basically there's also a duality between time and frequency. So that is, if you try to localize something in time, you lose localization in frequency. If you try to localize something, you can try to specify something in frequency, and you lose localization in time. Okay, and so this sort of thing, which is anomalous, also turns up, and that is the reason that people created these things called labels.